Resistivity of material. We have seen in the last video that if we have two equal samples of the same material, but we applied the electric potential on these two samples in different ways, we obtained different resistances. So in this case, the resistance depends on the material and the geometry. So instead of studying the resistance of the material, instead of the resistance R, we are going to study the resistivity of the material. Because the resistivity of the material is a character of the material. It is not a character, or it doesn't depend on how I applied the electric potential on this material. Okay? So we are going to define the resistivity of the material as the electric field inside the material, or the electric field between the two ends of the material, over the current density inside the material. The electric field inside the material over the current density inside the material. Or in other words, we can say that the electric field E is the resistivity of the material multiplied by G. And we should note that both the electric field and electric current density are vector quantities and are in the same direction. So the unit, or the electric field, or the vector electric field, is equal the resistivity, which is scalar quantity, multiplied by the current density G inside the material. Now, what is the symbol of the resistivity of a material? If we remember, the units of electric field can be represented as volt per meter, and the units of the current density G, ampere per meters square. So according to this, the unit of the resistivity rho would be volt over ampere, here meter squared in the denominator, so it would be meter square in the denominator over meter, so volt over ampere multiplied by meter. And we have mentioned that the unit of the potential, of the unit of the current, V over I, the volt over ampere, is ohm. So the unit of resistivity is ohm meter. So if we combine the SI units of the electric field and electric current density, we get the unit of the resistivity, which is ohm meter. Another parameter which is related to the resistivity is the conductivity. The conductivity is actually the reciprocal of the resistivity. So conductivity, which is abbreviated as sigma, resistivity is abbreviated as rho. Okay, the symbol of resistivity is rho, and the symbol of conductivity is sigma. Sigma is 1 over rho. Sigma, the conductivity, is 1 over the resistivity. So sigma is 1 over rho. And the unit of the conductivity is 1 over the unit of the resistivity. So the unit of conductivity is ohm meter to the power minus 1. And if we are talking about conductivity, it would be the reciprocal of the resistivity. So 1 over rho would be J over E. So in this case, J equals the conductivity multiplied by the electric field. Or in other words, we have moved rho from here to be 1 over rho here. So J would be sigma multiplied by E. So the resistivity and conductivity are the two sides of one coin, which represent the main characteristic or the electrical characteristic of the material. Okay? Example, for the value of the resistivity for different materials, if we are talking about conducting material like silver or copper or gold or aluminum, we will find out the resistivity is very small value. It is in the order of 10 to the power minus 8. If we are talking about insulating materials like glass or quartz, we find out the resistivity is very, very large, of order 10 to the power 10 to the power 14. So these are the two extremes: conducting materials, which has very, very small resistivity, and insulating material, which has very, very large resistivity. In between, we can obtain some materials which are called semiconductor material. In semiconductor material, the resistivity is still small, but it is not of the order 8 to the power minus 8. It is only 8 to the power minus 3 or 4. So there is power 10 to the power 5 difference between here and here. And in some cases, it can reach up to 10 to the power 3. But it is still much smaller than 10 to the power 10. So in between the conductor and the insulating material, there are some category of materials called semiconductor materials. Now we have seen that the resistivity is a property of the material. The question is, what would be the resistance of a sample? The resistance of a sample is a property of the object. It depends on the geometry of the object, the way of applying the electric potential on the object, in addition to the resistivity of the material of this object. So to calculate the resistance of a specific object, it is required to find out its geometry, its resistivity, and its way of applying electric potential. So if we know the resistivity of a substance such as copper, we can calculate the resistance of a length of wire made of this material. How this will be seen. To calculate the resistance from the resistivity, we said that the resistivity is the electric field over the current density, G. And the electric field along a sample of length L is the potential difference between the two ends over the length of the sample. If you remember, the electric field is minus delta V over delta X. Delta V is the potential difference. Delta X is the length. So the electric field is V over L. And the current density J is the total current passing through the sample over the cross section area of this sample. So J is I over A. So if we apply this value of the electric field and this value of the electric current density, so the resistivity is V over L over I over A. Now, if we are talking in terms of the resistance, V over I is the resistance. V over I is the resistance. So in this case, rho equal the resistance R multiplied by A over L. Or in other words, R would equal rho multiplied by L over A. So V over I is the resistance. So in this case, R equal the resistivity of the material multiplied by the length of the sample over the cross-section area of the sample. That's why when we apply the electric potential from this side to this side and measure the current flowing in this way, we find certain value of resistance. And if we apply the potential difference from this side to this side and measure the current in this way, we will find another resistance. That's because in this way we have the length and the area, and in this way we have another length and another area. This explains what we have said before. If we have a specific sample, the method of applying the electric potential will introduce different values of resistance. Because if I am applying the potential in this way, this would be the length. But if I'm applying the potential in this way, this would be the length. Right? So in general, the resistance equals the resistivity of the material multiplied by the length of the sample over the cross area or the cross section area of the sample. As an example, the figure here shows three cylindrical copper conductors. Three cylindrical copper conductors. So all of them are made of copper. All of them have the same resistivity along with their faces areas and lengths. So these are the faces area and this is the lengths. Rank them according to the current through them. So it is required to rank the current according to the current greatest first when the same potential difference is placed across them. So I have the same different potential and I want what is the greatest current, what is the less current. All right, let us think to this. This has length L and area A. So the resistance here would be rho multiplied by L over A. So the current would be V over R. Assuming that R is rho multiplied by L over A. Now, the resistance here would be 1/2 L over A over 2. So in terms of L over A, this 3L over A. So the resistance here is 3 times of the resistance here. Now, here the length is L over 2 and the area is A over 2. So the resistance here is L over 2 over A over 2 is L over A. So this is like this. So the resistance of the first sample and the resistance of the last sample are the same. And the resistance of the second sample is 3 times the resistance here or here. So the current here or here, if it is I, the current here would be 1 over 3I. 1 over 3 multiplied by I. So A and C are the greatest, then B. Okay?